Hi, I wrote a system up on the board, and some people will call this an oxygen transfer reaction. Take a look at this reaction. SO2 will become SO3, so it's gained an oxygen, and that oxygen came from CO2. CO2 loses an oxygen to become CO. Some time ago, for some certain conditions, I looked up the K value, the equilibrium expression constant for this, and it's just under 7. Underneath this consideration, I put some concentrations here, and here's the type of problem that we'll see. A student goes ahead and adds some gases, and whether they add 2 gases, maybe all 4 gases, 3 gases, this system's going to come to equilibrium. And a nice little apparatus showing equilibrium can be the water separatory funnels again. Reactants over on your left, products on your right. These are at equal volume, equal level. They've reached equilibrium. If equilibrium is tweaked, if we go ahead and lift up, we'll see that Le Chatelier's principle where we'll see a shift. If I set this back down, it's going to shift to reach equilibrium. But what if the student went ahead and mixed some gases and the system is not at equilibrium yet? Like right there. How can we tell? Should we come back and measure gases again? Can we predict which way, how far and stuff? And all these are yes, we could do this. So I'll set these aside and show you that while the student is doing gases, I'm doing colored water. It's not at equilibrium yet. Maybe in about 20 seconds, this will reach equilibrium. So the student sets up a series of gases, measures the concentrations, and the question is this at equilibrium? Is this at equilibrium? And certainly our measurements will be used. Everybody in the world says K is equal to 6.76. What I mean by saying that is this value came from a table, it's been confirmed, people have done it for years, and they're saying this is the accepted value. Sometimes we like to say it's the answer or it's the right value. This is what evidence has shown. Now, if you match that number, you would say I'm getting the same thing, we're at equilibrium. If you take measurements and you're far off from this, you might think I've done something wrong or the system is not at equilibrium yet. We don't like to calculate K. What we like to say is let's set up products over reactants and calculate that, but let's not call it K because K is like reserved for the correct or the accepted value. So we're going to calculate Q, quotient, products over reactants. So Q, just like K, maybe you can think of Q as being your personal K, is equal to products over reactants. And in this case, the stoichiometry is 1 to 1 to 1 to 1. All we have to do is put 2 products over 2 reactants. SO3 is a product. CO is a product. Go ahead and write down the next 2. We have SO2 as a reactant, and we have CO2 as a reactant. 2 products, 2 reactants. There they are. Let's plug in our measured values. Now I'm going to set this up with brackets. On the top, SO3 and CO, 1.02, 1.67. On the bottom, we have 0.45 molar as SO2, and the carbon dioxide is 0.34. Please be careful on your calculators. When you do this times this divided by, and use some nice brackets because of orders of operations in mathematics. And I calculate this out to be about 11.1. 11.1. This is my experimental value, and my experimental value does not equal K. I'm off by a little bit. My K, my experimental K, my data says 11.1, which is a little too high. Let's take a look at 3 different cases we can have. Case number 1, if I had calculated my value to be exactly the same as K, I would go, hey, it's settled and we've reached equilibrium. So the system is in equilibrium or balance. The concentrations will remain constant. This case has Q as being greater than K. I'll put an asterisk here because this is the case that we just did for our particular problem. If Q is greater than K, our products, take a look at the math. Our products are too high. We have too much product and not enough reactant. So more reactant will form. And case number 3, which did not happen in the previous example, would be, what if we had calculated Q as being too low? If Q is less than K, why? Our Q is too low. Our number, our calculation, the number isn't big enough. It's too small. Being too small, it would mean that we need this to be larger, this to be smaller. We would have more products form. More product will form. Three different possibilities. The system's not at equilibrium. It'll reach there shortly.